Welcome back to Dr. Liu's VCE Physics. Today's topic is light as a particle from the NHT 2019 physics exam. Let's learn together. If teachers, parents, or students see mistakes in my explanations, please give me your feedback. Photon absorption occurs when electrons transition from a lower to a higher energy state. Since electron transitions A and B involve upward jumps, and B traverses a greater energy difference, B will result in the highest frequency observed in the absorption spectrum. In their experiment, Kim and Roger are observing an electron diffraction pattern produced by 50,000 eV electrons. Kim believes that 5,000 eV X-rays would yield the same pattern, but Roger rightly points out that X-rays of a different energy are necessary. A fundamental principle of diffraction is that identical patterns arise from waves with the same wavelength. Therefore, the X-rays must possess the same wavelength as the 5,000 eV electrons to match the electron diffraction pattern. This also means their momentum must be equal. However, given that X-rays are massless photons and electrons have a defined mass, their energies will diverge despite having the same momentum. The objective is to ascertain the energy of the X-ray. The crucial insight for solving this problem is that the X-ray must possess the same wavelength as the electrons to yield an identical diffraction pattern. Consequently, we begin by calculating the speed and then the wavelength of the electrons, utilizing their known energy. With the electron's wavelength established, the energy of the X-ray can then be computed. The question asks for the higher energy level from which an electron descends to level 3, resulting in photon emission. We can calculate the photon's energy using its known wavelength. By summing this photon energy with the energy of level 3, we can identify the initial energy level, in this case, it's level 5. How do the quantized states of the hydrogen atom provide evidence of the wave-particle duality of the electron? Please explain it. Electrons in atoms act like waves, not just tiny particles. For an electron to be stable in an atom, its wave must fit perfectly around the nucleus, forming a standing wave. Because only these perfect fit wavelengths are allowed, electrons can only exist at specific, fixed energy levels, explaining the quantum nature of atoms. This apparatus is used to investigate the photoelectric effect. The frequency of the light and the type of metal can be changed. We are asked to determine the stopping voltage. This crucial voltage is the point at which the ammeter's reading drops to zero, signifying that the applied reverse voltage has successfully stopped all electron flow. The process begins with the light's energy being transferred to the electrons, generating kinetic energy. Since the work function is provided, the electron's kinetic energy is simply the difference between the light's energy and the work function. To then find the stopping voltage, we divide this kinetic energy by the elementary charge. For ease of calculation, we'll express energy in electron volts, eV, which means Planck's constant will be used in units of eV times s. The emission of electrons by light requires the light's frequency to be greater than a threshold frequency. This threshold frequency is associated with the longest wavelength that can still liberate electrons. Consequently, we calculate this maximum wavelength directly from the threshold frequency to understand the conditions for electron emission. No photoelectrons are emitted if the light's frequency is below a threshold frequency, regardless of its duration or intensity. This directly supports the particle model of light, which predicts a cutoff frequency below which emission stops. The wave model, by contrast, would suggest that energy accumulation over time could lead to emission. However, The particle model correctly states that a photon's energy is frequency dependent and delivered instantly. Accounting for 21 of the total 130 assessment marks, the light as a particle section makes up 16.2% of the assessment. It is comprised of 3 short answer questions, collectively worth 20 marks, and 1 multiple choice question, worth 1 mark. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.